Hello. Well, thanks for coming to the talk. So yesterday in the keynote, I showed a demo of the C# job system and compiler tech, and it's a really cool demo where we're showing off this Boyd simulation. And what I'm going to show you today is how you will be able to write that kind of code yourself, how it looks like the code. We're going to dive a lot into actually some sample code, how it all works, and the kind of approach that you need to take in order to get that kind of performance. So the reason there are really two things we're doing with this new tech. One is we want to run as much of our code as we can on multiple threads. So we're using the C# job system to get these kind of speedups. We want to really simulate a lot of things in parallel. We want to split our work in small chunks of processes that we run in parallel to each other. And we want to do that safely. Now, generally, when we're writing multi-threaded code, or when we're trying to write high-performance code, there's really three things that we need in order to get great performance. Number one, we want to have control over our data and our data layout and the data that we really access on a frame-by-frame basis. That's actually the first part you need to do. Before you don't have that kind of control, you can't really achieve very much with performance. And so we have a lot of new ways of dealing with those kind of problems and a lot of really nice APIs to do that. All of our APIs that we're using in the C# job system, they are GC allocation free, and they make it very easy to control your memory. So that's one part. The second part is multi-threading your code. So that's the process of writing your code in a way that it can run in parallel on multiple processors at the same time, running asynchronously to the main thread, doing processing while the main thread is doing other work. And then lastly, it's about generating the most efficient code. So we want to generate SIMD code, meaning code where we have single instructions operating on multiple pieces of data in parallel, and we have done a lot of compiler technology to achieve that. We have some, and I'll get into all of these things. So first, let's take a look when we combine all of that, and maybe some of you didn't believe what you saw yesterday. So I'm just gonna open the profiler there. All right, let's take a look at that, and then we turn on the compiler tech. It runs fast, and you can really see the big difference that it makes when we're running that code, right? Let's take a look at that in the timeline profiler. So here we have a frame where we're basically running our Boyd simulation in parallel on all these threads, right? The timeline profiler has been in Unity for a while, and you used to be able to just see the C++ code, how it's running in parallel, how it optimizes engine code. But now we have this C# code running here. So here's our Boyd simulation jobs, and they're running on all the different cores. So that's cool. And then when we look at it here, this is the frames where I turned on the C# job compiler. And you can see these frames are significantly smaller. So these are only 4 milliseconds long, whereas the ones before, they were 66 milliseconds. And that's basically just the compiler tech optimizing the code, making it significantly faster. And overall, we're getting 110x speedup when we combine all these optimizations together. Compiler tech being 14 times faster. And to achieve that, you need to change a lot in your code. You need to change the way you're thinking about how you write code. But I think overall, it's worth it. Sometimes you may not care about performance. You care maybe about battery consumption. And for that, you can also use the C# job system, because the compiler tag actually lets you, since it generates more efficient code, it can simply reduce battery consumption, because that code can just run much faster, and then the battery can, then the CPU can go to sleep, and you save battery consumption on mobile. So there's a lot of ways in which you can use this system to make your game better. So what I want to do is really start from the top with some very simple examples of what you need to do in order to take advantage of the C# job system. So I'm going to switch to my Mac. All right. So the first part, when you're using the C# job system, it is all about taking care of your memory. And when we write C# jobs, we don't want to use the garbage collector. We want to have explicit control over memory. So we're introducing new container types. The first one, the simplest one and the most efficient one, is native array. It's essentially the same as an array, but it has a bunch of restrictions, and it integrates with the safety system that I'm going to show you later. You have here, we are allocating an array. We have 100 elements of type int, and we're also using a specific allocator label. So what this is about is that usually on the C++ side, when we optimize our code, we use these different memory labels to get better speed. Because when you have a manual memory allocator, you can specify upfront if your lifetime of this allocation is very short, very long, and the pattern that we use in Unity generally is temp allocations. Those are allocations that live for a short amount of time, basically from the beginning of the function to the end of the function. Then we have temp job allocations that are allocated on the same frame and deallocated at the end of the frame, and they can be allocated on the main thread and deallocated on a job thread, for example. And lastly, we have persistent allocations. Those allocations live for a very long time. And these allocations don't go through the garbage collector, they go through our C++ allocation system. The second big difference is, of course, you have to manually dispose them. And by manually disposing them, you're really taking control of the memory. You're controlling when it's allocated and when it's deallocated. And you don't have a garbage collector deciding for you when a good time for that is. You're doing everything explicitly, and that gives you a lot of control. And that gives you control over performance. Apart from that, assigning values, you do the same way as you would normally do with an array. You have an index operator, and it all just works. There's a bunch of different container types that we have. We have a native array. We have a native list. Native list, basically these container types follow normal ways of writing C# code. So this is basically the same API as the list API. You can add elements, you have capacity, you can remove elements, you can sort it, you have all kinds of utility methods. Native slice is a really cool container type that basically lets you get a part of another container. So you could just extract sort of a subsection of an array into a slice. And then we have native hash map. That's basically a key value store dictionary in C#. Very well optimized container for that specific purpose. And then native multi-hash map is actually one that you don't usually have in .NET, but that I find is really, really useful when writing game code. So in the Boyd simulation, for example, the way we do that, the way we figure out what Boyds are near other Boyds, because they avoid each other, right? We basically put things in a grid, and this grid is represented by a hash table. And then we just find the neighboring cells. And of course, you want a multi-hash table, because then you can have multiple Boyds in each hash table cell. So there's a lot of really useful use cases with the hash table with a multi-hash map that makes it really efficient to use. Now, the one big limitation with the C# job system that you need to get used to when you're using it and when you're writing high-performance code is that everything is structs. You're not using classes. If you put a class on a job, you will get an error message. You can't do that. And the reason for that is because we want to make it completely safe. We want to make it impossible to create any race conditions. And we can only protect that if we have our own container library and if we make sure that you are using structs to represent all your data. But I believe almost all game code can be written that way. It just requires changing the way you write your code a little bit. All right. So the big one is, of course, what does a job actually look like? So here's a very simple job. This job copies one array source to another array destination. And that is basically the simplest possible job you could write. So a job is always a struct. And it inherits from iJob, for example. And that makes you implement an execute function. And then in this execute function, you can put your job code. You can call methods, whatever you like. But all the data that you're using is actually declared in the struct. And that's the key part to making this safe, to making it easy to understand what your data dependencies between the jobs are. And that is what allows our job compiler to work, and so on. So you're declaring everything. But you're not only declaring the arrays that you're using or the variables that you're using. If I put a float here or something like that, the main thing is that you're also declaring how you're going to use this data. So you're, for example, saying, I'm only going to use this native array as a source. I'm not going to write to it. And that's very important when it comes to providing safety and optimizing the code. So you're basically declaring in your job how you're going to use it. And then there's a system that enforces that the things that you have declared, you're actually following those rules. So you're filling in the job data. You have a source array, a destination array, which you allocate with the temp allocator here. And then, because it is deriving from iJob, you can call the schedule function. And the schedule function gives you back a job handle. And this job, it's now kicked off, and it runs. And there's no concept of a frame here, actually. It just runs, and it takes however long it has to take. It is, by definition, always asynchronous. And what makes it not asynchronous is you, at some point, you got this job handle back, and then you call .complete. So basically, you're just saying, make sure that this job is complete. And then on the main thread, when after this line has executed, then we know this job has completed. And in this case, we know that once we have called complete on that job, then we know the data has been copied from source to destination. So that's pretty much the pattern that we follow in this job system. All right. There is a couple different ways of writing jobs. There's basically different job types that we support. One that's really useful is iJob parallel 4. So iJob parallel 4 basically lets you define a job which is automatically split into many parts. Basically, you get different indices. It's like writing a for loop, but your for loop can run in parallel on different threads. So in this example, we're just doing the same thing. This very simple example. We have a source array, a destination array, and we're copying at the index, we're copying to the destination data. So we're just doing the same work as above, but now this code can actually run in parallel to each other. This job is automatically split based on how many worker threads there are, based on how much work there is to be done. So when we schedule the job, we now have an additional parameter. We have to say, how many iterations should we perform? So in this case, we want to run 500 iterations because that's how much data we had. And then we can say, we want 100, we want to split into a chunk size of 100 elements. And so it's going to create a bunch of jobs where there's an inner loop calling this execute function for 425 times, and 125 times, and then it runs that loop, and then in parallel there's another job running, and it runs at index 125 to index 250, and it just subdivides this automatically for you and runs it in parallel, making it really easy to sort of like express this code that can run in parallel. All right. Another thing that's extremely important for writing jobified code that is efficient is the concept of dependencies. So dependencies is all about declaring when a job can begin executing. Because sometimes you have one job computing some data, another job using that data, and you need to make sure that the second job waits for the first. In the Boyd simulation, for example, we are having a job that calculates a hash table to put all these Boyds in the right buckets, and then in our job, we're just looking up these hash tables. And before we can begin working on the Boyd simulation, reading from this hash table, that work has to be completed. And that is expressed with a dependency. So the simple example here is we have an array, we have a destination array, we have our job again, we fill in the source array, the destination array, and we schedule it. So now we have job handle A that we get back. Now we have a second job that we want to schedule, and maybe we want to copy that data to yet another array. Now we fill in the destination, so that's the result from the previous job that we copied. And we want to copy to this new array that we created. And now when we schedule the job, what we're gonna say is we're gonna put a dependency on that first job. So now the first job, it will copy the data, and when it's complete, the second job can begin working and copy the data. Right? It's all about that two jobs can't at the same time work on the same data, right? I mean, that's the funky thing about writing multi-threaded code. You want to avoid any kind of race conditions where two jobs are writing or reading from the same data at the same time. All right, so you express that with these dependencies, and then the key part here is that you can then get a job handle back to that second job. And you can still call .complete on that. So now what happens is that it will ensure that both jobs will be completed. First, job A, and then job B. And they will always complete in that order because you put that dependency there. And if you don't put that dependency there, then they can run in parallel. And internally, the job system is really made for this concept of on-demand completion. So basically what actually happens when you call .complete, the main thread doesn't just wait for it. It will actually start working on completing that job and its dependencies, because it knows exactly what dependencies it has. So it can contribute work to it. So it's not like just putting a mutex log or something like that in there. It's actually contributing work, and it's not wasting anything. And it also tells the other worker threads, when the main thread is waiting on something, it tells the other worker threads, okay, let's reprioritize that job and all its dependencies because the main thread is waiting on it. And we always want the main thread. The main thread is always the most important resource because it might schedule more jobs. And so we are basically reprioritizing all these jobs that we're now waiting upon because we call job handle b.complete, and we're completing them before and not in the original order of the queue that you scheduled them. All right. So we have the very basics of a job, right? We have our containers, we have our C# jobs that look like this, with a really nice API that is allocation-free. We have our dependencies, and so let's take a little bit of a look at some demos. All right. So the first one I want to show you is just a small demo where we're basically just rotating a bunch of cubes and just starting with a simple example of how to do that in Unity, because that's yet another specialized job type. So if you want to write a job that changes a transform component, there's another special job for it called a iJob parallel for transform. And basically, in this job, you get an execute function with an index. So it's very similar to a parallel for. It's operating on an array of transform components. You get an index and a transform axis. So on a C# job, you can't just access all the other existing component classes that we have. We have dedicated structs that represent these transform components and other components safely. And so you have this transform axis, and you can write to the transform.rotation as you would be used to. You generate an angle, an axis angle vector. You have an array of speed values by which we're rotating, right? We have basically all these cubes rotating here, and each one defines its own component, basically, that defines a speed at which it should rotate, right? That's what we're trying to represent, like just a speed for each component, and with that we rotate. And in the job, we just write to the transform component. When we schedule the job, it looks like this. We create our Rotator job. We put an array of speed values in it. We set the delta time, because again, you can't just call time.delta time from the main thread, from a job. Because of course, delta time actually changes while the job might be running, right? I mean, a job actually doesn't have a concept of a frame even. So you have to extract out the delta time, put it in your job, and then you can safely use it. And then we're simply scheduling the job, and we're writing to the transform component. So what's really cool about this is that in the timeline profile, if we look at this, you can see here, there is this rotator system that schedules all these jobs doing these rotations. And it runs here on the main thread, and it just takes like 0.1 milliseconds. And after it, there's all kinds of other code running. There's the audio system, render texture something, bounding volume system, and so on. And they are just running on the main thread, while we're just running our code, updating our bounding volumes. And here, the blue bars, that's the rotation system. That's the rotator job, rotating these cubes around its axis and doing all that work for a batch of tons of objects. And what's really cool is we're actually not inserting any sync points here, right? We're just saying, schedule these jobs that modify these transform components. And they can kick off, and the transform component, it understands what a job is. And it associates it with that transform component or that transform hierarchy. And only when we need to access that data do we actually wait for these jobs to complete. So you can actually see here, what actually accesses the data in the engine is the bounding volume system. So because we have mesh renderers on these guys, that's why we need to update bounding volumes every frame, because they're being rotated, so the bounding volume might have changed. So we need to grab the transform component and update the bounding volumes. That's all of these bounding volume jobs here, right? They're updating the bounding volume, and they're tightly scheduled against the last rotator job. Once the rotator job is done, then the bounding volumes can be updated. And there's no sync point except for the very end when we're doing the culling, where we have to wait for these rotator jobs to complete. And that really gets a lot of efficiency, where we don't just schedule some jobs and then we wait on them and then nothing runs, and then we schedule some jobs and then we wait for it and nothing runs. Instead, we're just scheduling all the jobs and then they just run in parallel until something needs it. All right. So then I want to show you one other thing. So I have a I have this a much simpler Boyd simulation here, where we actually have these fish swimming around, and it's basically the same Boyd simulation scripts, but they're just driving mesh renderers and transform components and so on. And I want to show you what happens when we add some mistakes to this jobified code, right? Because in practice, jobified code, it's really the problem is it's very easy to make mistakes. It's very difficult to visualize exactly all your data access. Like if you have if you have this Boyd data, maybe somebody else is writing to that in parallel while you're reading from it, and it's very difficult to visualize all of that in your head. And so we built this safety system to make it impossible to make mistakes. So the safety system runs in the editor, and it immediately tells you when you make a mistake. So this is the Boyd simulation system here. We have a job preparing our Boyd data. So basically, we are producing this multi-hash map of cells where all the Boyds are. And we have the simulation job where we have a bunch of simulation state, and we just output some Boyd data. So it's this thing here. That's our output. And a Boyd is actually, in the simulation, it's represented basically just as a small struct. And all it has is a position and a forward direction. We don't need more, right? We want to deal with the smallest piece of data that we can operate on really, really efficiently. And so we have this component data array that we are writing into. And then we have our job, basically doing some simulation code. Let's take a really quick look at that. So as an example, here's the code that does the separation and alignment. So they basically swim in swarms, aligning with neighboring Boyds, and they separate from each other when they get too close to each other. So we have a hash table here. We basically take the position, quantize it into sort of a cell in this hash table, and then we iterate over this multi-hash map to find all the neighboring cells, right? We have the neighboring 7 cells. We look it up, and we just keep iterating in this hash table until we find a Boyd that is nearby. We calculate the distance in position, calculate the squared distance, do sort of a fall off, and then based on that, we separate them or we make them go closer to each other, right? So that's how you add that kind of behavior. But let's say we make a mistake. Let's say over here we have our 2 jobs, right? We're scheduling a job that creates that hash table, and we have our simulation job. Let's say you forget the dependency between the 2, right? You have to do that explicitly. But let's say you forget that. When that happens, we basically get these error messages. So you can see, actually, we're not even getting any of these Boyds simulating. Instead, we get this really nice error message telling us the previously scheduled job, prepare parallel Boyd's job, reads from the native array, prepare parallel Boyd's job source. And you're trying to schedule a new job, simulation Boyd's job, which writes to the same native array. And to guarantee safety, you must include a parallel Boyd's job as a dependency of the newly scheduled job. So it's really, the idea with this is really, we want to make it so that if you have never written multi-threaded code, this system will teach you exactly what you need to do to stay on a safe path. And so it's basically not possible to make mistakes if you always look in the editor, in the console window, and you always fix the errors that it reports you. And we have all kinds of different error messages. If you added a line like this on the main thread, maybe accessing this array of Boyd data, it would simply tell you that you need to wait for the job to complete before you can access the data. And so basically, there's this whole safety system around to make it rock solid, and it's impossible to create race conditions. There's, of course, right now, you have basically a couple of different jobs and a very restricted environment. And over time, what we're going to do is adding more different job types or like job integrations to it. For example, the NavMesh system, they are already working on a system where you can basically treat NavMesh queries as sort of a buffer. And you can safely use the NavMesh queries to basically do pathfinding on jobs and so on and so forth. The same about letting you write directly to graphics memory. So you can directly from the CPU, you can have procedural mesh generation, and you can directly write to the final memory that you want to modify every frame. And that's right now there's like 3 copies to get to that memory if you write that. And with that you will get massive speedups, and it will run asynchronously to the main thread. There's other teams doing, for example, animation integration, where we can do blending completely in C# jobs. So really integrating deeply into the playable API and into the blending system in Mechanim. Or there was a prototype that the physics team has been doing about doing raycast queries, asynchronous raycast queries shot off from the thread and then consumed on a thread. So all these things, as we add more features to Unity, we can just expose more and more to the job system, but we'll always do it in a safe way, so that if you make a mistake, we will tell you. And we will always keep it completely safe, because I really believe in Unity. I believe very strongly in this philosophy of Unity being a sandbox, where it's not possible to make mistakes. You simply, well, we simply try to give you always a good error message that tells you what you can do to improve the situation. We never want to be in a situation where we just randomly crash while some random memory was overwritten the day before you ship, right? I mean, we don't want that. Let's talk a bit about the C# job compiler, because I think the C# job compiler, multi-threading code is great, but actually the C# job compiler makes the system really, really compelling, because it's not only useful when you write, when you want to create multi-threaded code, it also is super useful when you just want to run your code on a single thread. You just want it to run faster and use less battery. So with the C# job system, when I have written code for the C# job system, I can simply put these attributes on it. So I have the Boyd simulation here, and you basically just say compute job optimization, and you put that attribute and your code will run faster. It's nice, right? And we'll make this work on a lot of platforms. So basically, we will compile your code for the target platform with the best optimizations. Our compiler is a very specialized compiler for this particular thing. And the reason it works is because we can focus on just a very small subset of what you normally need to do in a compiler. For example, we don't have virtual functions. We don't have a garbage collector. We basically don't have a real runtime. We just generate code that computes things, and then we run it really fast. And so we're really focused with this compiler on high-level math optimization and geometry optimization that we're doing. So this compiler actually understands the math, and because there's a single entry point into this job, we can just inline all of this code and put it all together, and we can see exactly what data you're accessing, what, you know, like, we can see if two arrays, which one you're writing to, which one you're reading to. You have these attributes to specify that I'm only going to read from it. And so we can take advantage of these things and auto-vectorize your code and just generate much better code where we basically take advantage of these SIMD instructions, where you can have one instruction writing to multiple pieces of data in parallel. And usually, that's actually very difficult to write code for. But with the C# job system, we can make that much, much easier. And you can basically focus on writing algorithms while the compiler takes care of optimizing your code. Whereas if you try to write high performance SIMD code, you usually have to use intrinsics in C++ and really learn a lot about how to write that type of code, and you end up writing code that is not very readable anymore in the end. Another really cool part is actually this one. So for Boyd simulation, for example, we don't actually care that much if the Boyd maybe looks this direction or 1 degree this direction. So if you have trigonometric operations, square roots, these kind of things, we can just automatically generate code that is lower precision. Because for Boyd simulation, we don't care about the precision. Maybe you do. That's fine. You can just use standard precision. Or you can use low precision if you really don't actually care about the precision at all, basically. So you can, per job, decide what is it you want, what is this for? I mean, like, do you care about computing the square root to the last decimal or not? And then the compiler will just figure it out and take advantage of these relaxed precisions that you said we should be taking advantage of. All right, so that's the C# job compiler, and that's basically where we get our 14x speed up from just compiling that code and compiling it in a very specialized way, taking advantage of that whole structure we have in these C# jobs. Maybe some of you noticed it when I showed, for example, some of the Boyds. We have a new math library that we want to establish as this. You can use the old C# math library, but this new one I think is much nicer. Basically, the idea with the new math library is that it's really modeled after HLSL. It has all the operations, you're used to it from it, and it's a very consistent and nice math library. And to top it all off, you even have half, half 2, half 3, half 4 to really compress your data into the smallest thing if you don't need that much precision when you're storing your data. And of course, the compiler can generate extremely efficient instructions to load from a half into a float and so on. We also have new functions that we don't have in the old math library, like select. So that's really useful if you want to write vectorized code to do to make it generate branch-free code, but also just little neat things like just specifying a reverse square root. You know, taking a vector and dividing it by the square root, that's pretty expensive on a CPU. But instead, if we just multiply by the reverse square root, a CPU can implement that much more efficiently. So those are just kind of the things that we expose in the new math library that we can then really take advantage of in the compiler tag. All right, so the big question with this is then, of course, we have all this cool shit. How are we going to write game code for it? And how are we going to make that easy? And I want to take you through the journey of sort of like, after we had written like some of these systems, of how we think we can write game code for it that is actually really nice. So let's start out with what we have today. We have this very simple example of a rotator component, right? This is how you write a component. And we all like components. It's really nice. You drag and drop them on game objects and they do their thing. We want designers to use pre-made components. So you have this update function. It runs. It does its rotation. We rotate by the delta time and so on. And of course, the problem here is that none of this is done in batch. The memory layout is all over the place. And these update functions aren't very inlined together, and they're just kind of happening randomly during the frame. So the first thing that comes to mind when optimizing that, and some of you already do this. So basically, the first thing that you would do is to optimize it is actually not jobifying it. The first thing is you take control of your data layout. You want to tightly pack your data and access as little as possible to get these big speedups when dealing with big amount of data. So we still have a component. We have a script, we have a mono behavior, we have a manager that is part of the the component, we have a speed value, and we have an index. So we're basically registering ourselves with sort of an array of transform component and array of speed values. Right? So basically, when we enable the component, we add ourselves to the manager. When we remove ourselves from the manager. I'm sure a lot of you have already actually, who has done this kind of optimization in their code? All right, cool, great. So we're adding to these two arrays that are kind of in parallel to each other. We add the speed value, the float, and we add the array of transforms. And now, when we have our loop, that means we can just iterate over that array of transform components, assign the rotation, and when we read the speed value, we're actually not looking up, first give me the rotator component, and then there is a float in there and jumping all over memory. Instead, we just have a tightly packed array of floats, and we're accessing them in linear order. And that's what the CPU likes. The CPU likes it when you're reading data completely linearly, when it can parallelize reading that memory in while you're doing your operations and all that good stuff. What the CPU hates is if you, when you do this math operation, you're like telling it, hey, I need that float, and then you're reading it in. That's what causes really big performance issues. And so when you structure your code in this data-oriented design style, you get very, very big performance improvements without even using the C# job system. So we basically have this array, we iterate over, we apply our rotation. That's cool. Now, the next step then would be, all right, cool, we're just going to use the C# job system. So it's basically the same. Instead of using a list of transforms, you use a transform access array. You add a transform component, you add a speed component, and then we just schedule a job. We put the delta time there, we have a rotator job, we have our array of speed values that we're going to use in the job, and we apply our rotation. Cool, right? We have basically, we have a very good memory layout, we have jobified code, and we can, on this code, we could enable the C# compiler tag, and we would get massive speed up. So that's cool. Okay, but the problem is we wrote 120 lines of code in order to work with our data-oriented design style code. And this object-oriented code, we have, I mean, excluding these, we have like something like 20 lines of code. So that's not cool. We want to make it easy, right? So there's an idea of how we can write code differently when we care about writing this kind of game code. And the idea is this. The idea is, let's separate the behavior from the data. So there's a component, a rotation speed component. All it does is it stores the speed. It does not define the behavior at all. It just stores the data, right? So that I can attach it to a game object. And then instead, you have a component system. The component system is responsible for tracking a set of components and then iterating over them and applying rotations, all kinds of things, whatever you want to it. And so you can see here, we end up with roughly 25 lines of code. So just a little bit more than the object-oriented version. And that's actually quite concise code now. And I think it's a little bit nicer to read. Maybe it's because I'm very used to writing data-oriented design code, but actually the separation of systems from data, I think it structures the code in a nicer way. So what's actually happening here, though? The trick is we have these tuples. So the tuples is what essentially replaces a get component call. right? If you look at this rotator, what actually happens here is we call getComponent, transform, and then we apply a rotation, right? That's what's really happening behind the scenes. It's just that there's a nice accessor for it. And what's happening here is the system maintains two arrays for you automatically because you put this attribute, inject tuples, on it. And basically, these two arrays, it will fill with transform components that have both of those components. So it will only put something in this component array if there's a transform component and if there's a rotation speed component. And now these two arrays, they are in parallel, and at the same index, they refer to the same game object's components. So that's why we can write this for loop over the transform components, and we assign the transform component, and then we assign the rotator speed, right, at that index. And now we don't have a getComponent call. It's basically cached automatically for us. And that's what actually gets this code in a state where it's really quite simple again. Okay, now, the problem is this one, we still have our mono behavior, we still have our memory access all over the place. So the final step is then a struct-based component. So that's a new component that we want to introduce that is basically a lightweight component that actually doesn't live sort of in a mono behavior anymore. It actually lives in a manager that automatically manages all instances of rotation speed for you. And this manager knows what game object it is associated with. And if you look at this code, the rotating system, you then see the only difference compared to this code here, because we changed this one to an iComponent data, this one becomes a component data array. And internally, a component data array is basically a pointer to that manager's array of data with the index remap table on it. And that's it. And that gives us a lot of control over laying that data out the perfect way, optimizing our data, and accessing it in the most efficient way. Now, to jobify it, you then take the final step, which is basically you use this inject tuples instead on a transform access array. You have a component data array with the rotation speed, and you put that data directly on your rotator job. So here we have our component data array with rotation speed, and we get the speed value from this array, and we write to the transform component that is passed to us in the job. And when we do that, that is where we get massive speedups, because we're not asking the transform component to give us the internal representation of the transform component, and like all these cache misses that we're introducing, we're just going directly to the thing. The transform access, that's a pointer to the hierarchy and an index in it. So it's basically low-level system talking to low-level system in the most optimal way. And then there's another part here that we're doing that makes this writing this jobified game code much easier. So that's, in this one here, we derive from component system. And in this guy, we derive from job component system. And one thing that can be difficult when you have all these jobs in flight and this data that is you know, like a rotator, maybe somebody wants to modify the rotator component speed value from the main thread or from a job even. And managing these dependencies, that's difficult. So what we're doing, because you're anyway declaring your data dependencies in the component system, we can just tell you this is the dependency you should schedule your job with. So you basically say, whenever you schedule a job, you just follow this way of doing it. You schedule a job, you call getDependency and put that dependency in there, and when you have scheduled the job, you call addDependency, and that's it. Then you have written a job that is completely safe, that that basically you could, from the rotator component, change the rotator speed and everything would work perfectly. No race conditions, nothing. And it's quite concise, because we basically have, to end up with this jobified code, we have roughly 50 lines of code now. Right. Yes. It's pretty cool, right? All right. So, where were we? Was there more that I should talk about? Right. So that was basically the walkthrough. And I hope with that you can really see how it's going to be possible with all these things coming together to write practically all game code jobified. Now, it's of course, maybe you don't want to do that, and that's fine. But the important part to realize is that I think you can. Because with the safety system, you can actually rely on that, that your code is safe, because somebody's checking it for you. And it's very difficult, it's basically not possible to make those mistakes. And that's usually why people don't jobify their code, or why maybe a senior engineer would tell a junior engineer, don't do that, because you probably don't even understand the complexity that is involved in making this jobified code safe. But with the system, that's taken care of. So then, of course, the big question is when? And the idea is that we will roll this out in stages. So the C# job system, we're planning to get that in 17.3. So that will hopefully ship this year or early next year. And that's basically the core of the C# job system. The component system, actually right now, that is all in project. So we will give a project out where there's sort of an early version that you can already play around with and that you can actually just modify. And then slowly we will roll that into a more official system with all the optimizations that we can do if we integrate it a little bit more. The math library, that's actually also something that we're going to put into that project folder. So you can get an early access, try it out, see how you like it. And then finally, the C# job compiler, that's still taking a while longer. So that will ship in stages. I don't know. It will definitely not be this year, that's for sure. But basically, we are working very much in parallel on on these different components. All right, that's actually the overview of all this cool shit we have been baking. So. Yeah, I hope you like it, and I think we can take some questions now.
Hey, thanks for the great talk. Yeah. I have one question. So the performance gains, we had this ridiculous bar yesterday.
Yeah.
They depend on the platform, I guess, right? Because you have different processor architectures.
Right.
How is it with the cell broadband architecture in the PlayStation 4, for example?
Well, so on the PlayStation 4, we have 6 cores. So basically, you would get a 6 times speed up from. I mean, on that particular code that you jobify, that can run 6 times faster because the job system can run it. So that's one gain. But generally, the speedups we're getting from the compiler tech, that's roughly around 14x. I mean, it very much depends on the type of code. The more math-heavy your code, the better it will work, of course. But I mean, roughly, that's where it's at. I'm pretty confident on that.
Awesome. Yeah, I look forward to it. Thanks.
Yeah.
Very cool demo. One thing I have in mind is when I saw the native list and array, it would be good if it can be also directly serializable.
Yes.
So we don't have to do extra copy.
Yes.
That's it.
We definitely will. We just don't have that yet, but totally necessary, obviously. Yes.
Yeah. So the entity component system you showed,
Yep.
The update function was called automatically by Unity.
Yes.
Is there a way to call it yourself? Because I like to structure the updates, so I know when everything is.
That's the part I didn't show. That's the coolest part. So,
okay.
So we're actually working on exposing the player loop as a set of callbacks that you can reorder as you like. How about that?
Nice.
Because basically that's actually when you jobify code, that's a really important thing, because you want to, when you jobify code, you need to be able to move the scheduling of jobs early and the waiting on jobs late if you really want to take advantage of that asynchronicity, right? If you want the parallelism. And so that control is super important.
Hey, so with your new maths library, is there any consideration to support double precision vectors and maths operations?
Not yet.
Okay.
We haven't really thought too much about that yet, no.
No worries. Yeah, just for large open world sort of space simulation games,
right.
Often you're required to, there's not enough precision in the 32-bit floats, so often there's a bit of overhead trying to use a floating origin approach to deal with that.
Right. But would that actually help you in the end?
It just means there's less overhead, having to have your own custom implementation of the...
What I mean is, if the transform component is in float, would it help you to have double in the math?
Well, the way we approach it is that all game objects have their own variable which is in double precision, and then we each frame we set that relative to the camera that we center at the origin.
I see.
And we could jobify that process so that that was just my general thought. So it would be good to have that those double precision vectors out of the box as opposed to additional.
That makes sense. I will bring that back to the team. That's a really good point.
Thank you.
Thank you.
Hi. Could you share some insights how you came up with that? What inspired you, or what?
That's a great question, actually. Well, I mean, there are really two parts. So there's the compiler tag. And I mean, when you look at this code, I mean, you can see a lot of parallels to compute shaders. So that's part of it, of seeing that and just thinking about how that could apply to C# and how we could express that in a really nice way. And basically, we did this at one of our hack weeks. We just tried it out. I mean, it just seemed like, we just asked the question, how can we beat the shit out of C++ performance? Then we sat down and tried. And then we started writing compiler tag. And we have quite a few really brilliant compiler engineers in Unity. And then sort of over time, this formed. And then we put a team together and started building it. And the C# job system, on the other hand, it's actually pretty interesting, because we do this onboarding at Unity, where we actually where we spend a lot of time teaching programmers, and we always teach them how to write jobified code, because that's very important in the engine. And I've been teaching that for 1.5 years, and basically saying the same things again and again and really explaining things, it sometimes helps you understand what's the fundamental nature of sort of jobifying code. And the concepts of how to make safe multi-threaded code is actually relatively simple. The hard part is enforcing it and not making mistakes. And that can actually be relatively easily expressed once you get it. So I don't know, it just came up through doing that onboarding again and again, and seeing people fail at jobifying code and making all kinds of race conditions that are really easy to find when you, in a structured way, analyze the code and look for mistakes. And then codifying it, we just, we do a lot of cool stuff at Hack Week, so that was another Hack Week. We just spent a week and tried this out, and it worked. It was amazing. But yeah. And then we had a system that's safe, and that was kind of the core of being able to do it, because I am very anal about this kind of code having to be safe. I don't think we could ship that without it being possible to you know, like it has to be possible that the code is race condition free. If you can't do that, it doesn't pass my bar.
Good job anyway.
Thank you.
So I have a question about the job.
Yep.
Does the job always need to be completed in the update, or can the job oversee a frame actually and and can check later that it's done?
Right. So you can schedule a job, and a job has no concept of a frame. If you schedule a job that takes 20 frames, that's fine. No problem at all. What makes it frame dependent is you calling complete at some point. And that can be anywhere.
Okay, can I also check when it's done?
Yes, there's a function called isDone, and that basically tells you, are you done yet? So basically, we use that, for example, for the navmesh baking API, like these more actually asynchronous APIs that are sort of like running in the background. We just schedule those as jobs, and then every frame, if it's done, then we send these events that tell the system, hey, now you're done, integrate yourself, hook yourself up, and that work we usually perform on the main thread.
Okay, thank you.
Yeah, thank you very much. While listening, I had the feeling that I'm listening to someone who tells me how to use the modern .NET async await features and combine them with embed native C++ code wherever it is necessary to write performant code. Did you ever think about separating these two things so that when you are not bound to performance, you can keep on writing simple C# code? And if you have a really big project and performance really matters, just start writing performance C++ code in such a great environment that you now build up?
So the question is...
It's like, okay, you're combining two very cool things, like the asynchronous handling of the modern C# with async await, and on the other hand, give us access to C++ highly optimized code, or being able to write this in Unity.
Right.
Have you ever think about if it would be an enhancement and less work for you if we would write the high-performance code directly in C++ and not in C#?
Right. Well, I strongly believe that we will be able to write code in C# that beats C++ code by a very wide margin.
Okay, I'm very curious. Thank you very much.
So that's why I don't think we need to go there. I mean, in fact, the demos we're showing, it already does. So, yes.
Well, just a second for support for double precision.
Cool.
Just a quick question. When you were showing off where you had the transform, you were editing the transforms, does Unity auto-complete the job for you when it needs, like, for example, if you had a mesh collider on it, does it auto-complete when it's required to have that mesh collider and calculate the physics? Yep. Or do you have to complete on, like, late update or something like that?
No, so that's totally automatic. So these systems that are built into Unity, the transform component understands jobs and the job handle. And when you, for example, call transform.position, what happens is that, because the conceptual model in Unity for these jobs is that we do on-demand completion. When you schedule the job to the main thread, it should appear as if that work, that job that you scheduled, has completed. So we basically, when you call transform.position, that's when we call job.complete from the C++ code, waiting for those jobs to complete. And this code is highly optimized, so if you call it multiple times or something, it's basically one branch with one lookup. It's extremely efficient. So we can do that in very high performance cases.
Cool, thank you.
Yeah.
Hi, two questions. One, will we be able to use the native containers in ordinary code just to get around garbage collection?
Yes.
That's totally cool. And two, what's the reasoning behind the half precision float? Because I imagine if you don't have CPU support for these, those won't be very efficient.
Well, when you start writing really high-performance code, the biggest bottleneck in the end, often, when you start taking advantage of auto-vectorization and your code is really as tight as it can be, usually what happens is your bandwidth limited in terms of loading the memory from the RAM into the registers. And the more you can compress your data, the better. And half precision lets you turn a float into 2 bytes. And so that can basically make your bandwidth, basically you can put twice as much data if you don't need the precision.
Okay, but the CPU will mostly be doing single precision anyway.
Yeah, so usually what happens is that if you put it in a native array, it will load it, and then it will do full precision math on it, and then when it has to write it back, it will convert it back.
Very cool, thanks.
Yeah.
Hi, thanks. I just caught the tail of your presentation. Unfortunately, it was a long line. I'm curious do you have to worry about race condition? You talked about the interesting architecture of this job system.
Yes.
And also, I'm trying to understand, can you time stuff together, like a timeline? I don't know, in threading you use gates, and then you can time stuff together. I'm just trying to understand what will be the race condition you will have on.
Right, so there's a full system in there that makes it impossible to create race conditions.
Okay.
And that detects any of the race conditions that you might make.
How about if you have shared resources? Will you have shared resources with
Yes.
different jobs?
That is what this safety system does.
Okay.
It's pretty cool. You should watch the talk.
All right.
All right. Well, in that case, thank you very much.